I will explain you this theorem in this video, theorem 6.1.2. Here you can see the statement. If V is finite dimensional over F, then T belongs to A of V is invertible if and only if the constant term of the minimal polynomial for T is not 0. So this is an if and only if statement. So you are assuming this first. Sorry, you are assuming this first in the first part. Okay. The converse, oh my god, I am blabbering. Okay, you are assuming this. Okay, the constant term, just rewrite it down from the statement, copy it down. So here that line is incomplete because okay, this is the notes that I have made for my learning, right? So the sentence is not complete. This is what we are doing. In assumption, you are rewriting the sentence here, and to prove, you are writing T belongs to A of V is invertible. That is, we are going to prove this T is invertible. So to prove this T is invertible, what we are going to do is, we are going to prove T is equal to S, T is equal to 1. By the definition of invertible, it is enough to prove T is, to say T is invertible, we can prove T is equal to ST is equal to 1. This is what we are going to prove. Let's see how to prove this. Using this, that is using this, you are going to prove this. So first, to proceed further, first you have to take a minimal polynomial, right? So that is what you are going to do now. Let the minimal polynomial is denoted as P of x. Let P of x be a minimal polynomial for T over F. This is the sentence you have to write. This is the minimal polynomial, alpha naught plus alpha 1x plus alpha 2x square plus x at alpha k x power k. Here alpha k not equal to 0. That is the condition. Okay, because if alpha not equal to 0, the degree of this polynomial will get decreased. That don't want to happen. Okay, so that is why this condition is must. Now this is a minimal polynomial. That is how you have to write. So minimal polynomial means T satisfies this polynomial. Okay, if T is having T does not, that is, the meaning is this is a minimal polynomial, therefore T satisfies this polynomial. If any other polynomial having degree less than this k, then T does not satisfy that polynomial. Okay, that is what the concept you are going to use in this proof. That is why I am telling that in advance. So here P of x equal to, you are taking a minimal polynomial. This is minimal polynomial. Therefore T satisfies this polynomial. That is why you are writing this P of T is equal to 0. Now in the place of x, in the polynomial, here in the place of x you are substituting the value of t, so that you will get this equation. Now you are using the assumption. In the assumption they have given you alpha naught not equal to 0, so you are using that in this equation. So if alpha naught not equal to 0, in this line you are bringing this alpha naught to this side, so that you will get this. Now you are to bring 1 here, you are multiplying minus 1 by alpha naught in the next step, so that you will get this. Now from this you are taking t outside, so that you will get this step. You are just taking t common. That is what the only difference you are making. So at that time here the degree will become k minus 1. That you should note this, otherwise you commit mistakes in this line. Then what you are doing is you are bringing this t to this side, okay, is equal to 1. Therefore from these two lines you can write t. Consider this is the value of s, okay, t s equal to s t is equal to 1. In both cases you are getting 1, right? So that is why you are writing this line. So you have proved what you have proved to say t is invertible. So the first part is over. Now we are going to prove the converse part of this theorem. So assume what you have proved in the previous part, and to prove what you, in the prove line you have to write what you have assumed in the first part. Did I tell correct? Okay, assume T is invertible, and you are going to prove the constant term of the minimal polynomial for T is not 0. That is what we are going to prove in this converse part. So here write it down from the question. And suppose you are going to bring the contradiction at the end, okay, the proof is of that kind. So you are taking, suppose alpha naught not equal to, sorry, you have to prove alpha naught not equal to 0. So suppose alpha naught equal to 0 means our equation 1 will becomes, here in the place of alpha naught you will put 0, so that you will get the remaining terms. So write it down. Now from this you are taking t outside, so that you will get this t common, so that you will get this. So since t is invertible, in the assumption you have, you are using assumption here, t is invertible, we know if t is invertible, inverse will be exist, t inverse exists. So here you are multiplying with the t inverse, so that you will get this step. Now t inverse and t will become 1, so that you will get this step. Now you are giving name to this polynomial, that is q of x. Okay, now using that you are going to write a sentence. T satisfies the polynomial q of x equal to this. That is what happening in this line. Okay, because here it is, you are writing this polynomial with the t, and this is satisfying this polynomial. How? You are getting equal to 0. So from this you can say this t is satisfying this polynomial. The name of this polynomial is q of x. Since degree of, here look at this polynomial, in this polynomial the degree of q of x is k minus 1. It means it is less than the degree of the polynomial p of x. Our degree of the polynomial is, degree of the minimal polynomial p of x is k. But here you are getting another one polynomial q of x, its degree is less than less than the minimal polynomial, less than the degree of the minimal polynomial p of x. Also it is satisfying t. Okay. Okay, since degree of q of x is less than p of x, we are getting a contradiction. Okay, we get a contradiction to the fact. To what you are getting contradiction, that is what you are writing in this line. P of x is a minimal polynomial for t. What is the condition? Here you are taking P of x is a minimal polynomial. It means t satisfies the polynomial having degree this. T does not satisfy the polynomial having degree less than k, but here t is satisfying. So you are getting a contradiction. Therefore you can say our assumption is wrong. Therefore you get alpha naught not equal to 0. This is what you have to prove in this part, right? So you have proved what they asked us to prove. So hence the proof.